I'm Saritha Kumari, Assistant Professor, EEE Department, working in Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today, my topic is capacitance of a three-phase transmission line. So, it is related to course outcome 1. So, a three-phase transmission line we can see on the right side. So, there are three conductors A, B, okay, A, B, C. Three conductors are shown with small alphabetical letters. So, and there are two things here for a three-phase line, as we know. The spacing between the conductors may be equilateral or are not equilateral. That means so. First, we see the with equilateral spacing. The distance between the conductors is equal. With the distance between any two conductors, if we take, all are equal. So that's why here we can see distance between the first two conductors AB is capital D, then between BC conductors also small d, then the third one also the small d only. So now, so first we start with, as we know, in my last lecture we have seen for a single phase transmission line how it is started. So we first write the potential difference between the conductors, any two conductors here, because it is a three-phase line. So first we write the potential difference expression. Then based on the capacitance definition, we substitute in that, then we get the final expression for capacitance. So to write the potential difference expression, so basically consider when there are group of conductors, as we know this, when there are group of conductors starts from 1 to n, maximum number in that group, the conductors are up to n, capital N. Then the potential difference between the ith and kth conductor. Ith and kth conductor is given, okay, due to due to due to all charges present in that group, okay. There are group of conductors starts from 1 up to n, capital N. So we are writing, this is the expression for potential difference between the I and K, between ith and kth conductors. So that is given by like this. So here 1 by 2 pi epsilon qm, so where m varies from sigma 1 to capital N, okay, log of capital D I m by capital D K m. So volts, units. So now, so here based on this expression, first this is the expression given potential difference between the conductors AB, between the conductors AB. So see that here this is epsilon, okay, this is from the textbook. So notation may be small different from textbook to textbook. So as well, this is epsilon, like above expression only, okay. So between the conductors AB, so that is given by, because there are three conductors here. As you remember, based on this expression, for a single phase transmission line, if we write the potential difference between them is given by V12, right? That is given V12, right? 1 by 2 pi epsilon for a single phase line. I'm just recalling, single phase line, the potential difference between two conductors, okay, is given one, first conductor and second conductor, okay. So based on this expression, q1, first initially m is 1, log of I is 2, right? So 1 by d2, 1 by 1 plus, when m is equal to 2, log of d2 2 2 by 1 2, right? So that is for single phase line. There are only two conductors. So this is the expression. So in this D21 is equal to D12 is equal to D, spacing between the two conductors, capital D, okay, and D11 is equal to R1, right, radius of a first conductor, its own radius, and D22 is second conductor radius. So from this, the expression for V12 is 1 by 2 pi epsilon Q1 log of D by R1 plus Q2 log R2 by D, right? So, similar manner here in the three phase, if we see the three phase line, VAB between conductors AB is given by 1 by 2 pi epsilon, okay? So, this is here, first charge is okay, QA. So, with respect to conductor A, its own charge is QA log of capital D by its, okay, what is capital D? Distance between the conductors AB. Capital D by its own radius R. So assume that the radius of all conductors is same. Okay, R1, R2, R3 are both, all are equal to R. Then, okay, like this expression, first term. Then with respect to the second conductor, because this is a V12 between, right? So second expression, second term is with respect to second conductor. So similar manner here also VAB we are writing. So first term already over, then second term is with respect to B conductor, QB plus log of the conductor radius is, okay, R, right? This is the numerator, that's why R by down the distance between the conductors. Next, third component with respect to the third conductor QC, right? Charge is QC and log of the distances, okay, the distance from the conductor CAB. So, which is nothing but both are capital D, capital D. Okay. Okay, this is how VAB is written for the three-phase line with symmetrical spacing. Next, VAC, okay, voltage between the conductors A and C. So, 1 by 2 pi epsilon QA, first term is with respect to conductor A, QA log of D by R, okay. Then second term is with respect to conductor here C, right? So that's why first one is okay like above. So C conductor C means QC log of smaller by capital D, and due to conductor B there is no B, okay, B conductor here in the picture. So that's why QB into log of numerator and denominator both are with respect to distances, okay, distance of the distance between the conductors. Okay, now adding both VAB and VAC. So that is given by what is a 1 by 2 pi k is common. So QA is two terms, two components. So 2 QA log of capital D by smaller, and if we see QB, this one, okay. So QB has two terms, log A plus log B becomes, okay, like that, and similarly QC also what it will become, okay, log of R by D. So after simplifying that, so for both, after again rewriting this, QB, QC have the same term, log of R by D. So the expression simplified one is like this. Now, for a three-phase conductor, okay, balanced three-phase line, the total current is equal to 0, right? Total current, that means the sum of the three-phase currents is equal to 0. That means I1 plus I2 plus I3 is equal to 0. That means we can say IA, IB, IC. Here we have taken phases are not 1, 2, 3, A, B, C, right? So IA plus IB plus IC is equal to 0. If we write in terms of charges, QA plus QB plus QC is equal to 0. That means QB plus QC is equal to minus QA, right? So this is VA, this is VA and VAB and VAB and VAC sum addition. This is the expression. So in this, now next step we substitute. Okay, QB plus QC is equal to minus QA. So simplified after that, what we get it as, okay, what we get, 3QA by 3QA by 2 pi epsilon naught log of d by r. Okay, now this is, okay, the final expression of the sum of both AB and VAC. Now, for a balanced three phase, okay, voltage. So the, for a three phase balanced, okay, system in terms of voltages, this is, okay, let us say voltages, these are line voltages, VAB, VBC, VCN, then these are neutral voltages, right? VAN, VBN, VCN. Then VAB plus VAC is equal to 3 VAN, right? Because we know that what is VAB? VAN minus VBN, right? VAB can be written as VAN plus VNB, right? Now, VAN plus VNB. Now, VNB can be written as minus VBN, right? So, that is how. Next, similarly, what is VAC? VAN minus VCN. Now, if we add both, what we will get? What we will get? VAN 2 VAN minus of VBN plus VCN. So, what is, okay, we know that the sum of the three voltages is equal to 0. So, this will be become plus VAN. Okay, VAN plus VBN plus VCN is equal to 0. So, sum of these two will be equal to. So, that's why this is a final expression. VAB plus VAC is equal to 3 VAN. Now, okay, these are the basics for a three-phase balanced system. Okay. Now, next step. So, equate the. This is one thing we already, okay. We already derived it, and also for a three-phase balanced system, we know that the sum of these two voltages will be equal to 3 VAN. So next, what we do is equate the two. So what we, because the left hand side terms are equal, so the next thing what we can say, VAN is equal to okay, 3 not 3 gets cancelled, so QA by 2 pi epsilon. Okay, this is K means epsilon log of capital D by R. So this is a voltage, okay, in case of a three phase line with symmetrical spacing, okay, neutral voltage. Now, because basically we have the definition for capacitance is the ratio of charge to the potential difference. So VAN already we have written the expression of it. So here finally substituting the equation of capacitance. So that is given by, let us consider we are writing for first conductor. So QA by, that's why charge considered is QA by VAN. So VAN, if we substitute here, Q gets cancelled, 2 pi epsilon comes up. So 2 pi epsilon by 2 epsilon naught by log of capital D by R. So this is the expression for capacitance in case of a three-phase line with symmetrical spacing. If you recollect, the for a single phase transmission line also, in my last lecture, this is the same expression we have for the for a single phase line. Now, if you write the same expression in terms of log base 10, okay, this is expression 0.024 by log base 10 capital D by R microfarads per kilometer. Now, if we want to write the charge current, okay, charge current, what we will write, because in case of capacitor the charge current is given by V by XC. So V is what? J 1 by J omega C. So here J omega C. So what is voltage? Neutral voltage, phase to neutral. Capacitance also with respect to one conductor. So that's why the charging current is calculated as C J omega CN. Okay, VAN, CN or CAN. So that is how the capacitance for a three-phase line, okay, is calculated. Okay, capacitance expression for a three-phase line with symmetrical spacing is calculated, which is same as a single phase transmission line. Okay, charging current also. Okay, only the thing is here just uh, keep in mind the voltage is neutral voltage. Okay, because capacitance neutral voltage for phase voltage, that means, right? Because capacitance we can consider for capacitance of the one phase. Okay, with respect to neutral. Okay, next another case. If we consider three-phase line with unsymmetrical spacing, okay, unsymmetrical spacing means, as we know, the distance between the conductors is not same. It is unequal. Okay, that is called unsymmetrical spacing. So if that is the case, what we do, so we know that the same thing we have seen when the three phase line with unsymmetrical spacing is there they implement the transposition concept. So in the transposition, what they do is the total length of the line is divided into three parts. Okay, so here you can see the how the total length of the line. If we say, okay, this is the length of the transmission line, total length small l. It is divided into three parts like this. So each they say that there are positions, three positions. Okay, first position, second position, third position. Each position length is equal to L by 3. Okay, like that. Now, transposition means transposition. That means if a line is transposed, means each conductor takes takes all the positions of the conductors. Each conductor takes all the positions of the conductors. Here, each position is the one third of the total length of the line. So you can see this is a unsymmetrical spacing, okay, of the three conductors A, B, C, and distances between them are between A, B. It is given by D1 to capital D suffix 1 2. Between the second and third conductor D2 3. Then okay, like that. Now first position, the conductor's position is like this: A, B, C. Okay, on the top first face is there A, B, C. Next, then the next position A comes down one level down. So here next level A, B also comes one level down. C next level go, okay, comes down. So up it comes C. Next, that is a position 2. And next third position, again phase A comes one more level down. So it comes completely down A. Then B also comes to next level down. So B comes up here and C comes here. So this is how the transversal line is represented. Now, again, consider the balanced system. So, accordingly, QA plus QB plus QC is equal to 0. So, here again, first we write the expressions for voltages, potential difference between the conductors. Then, um, using that, we finally give the expression for capacitance. So, to write the potential difference equation, again consider the um, consider the expression in a group of conductors, the distance, the voltage or potential difference between the ith and kth conductor. Okay, that is the expression as we know, because just now we have seen that. Now, for this case, first they are writing potential difference between the phases A B for the first position. Okay, there are three positions, right? So for the first position, VAB is given by, okay, 1 by 2 pi epsilon QA, okay, into log of what, with respect to A conductor, it becomes the numerator, it's capital D term. So distance between the distance of conductor A with respect to B conductor. So D12 and the denominator smaller. Then QB is given by log of smaller comes up like previous how we have written. The same manner we write the terms here smaller by capital D 12. Then QC is it is nowhere in the picture. So we just consider the distance of the this third conductor with respect to first and second conductors. Okay, so QC log of D23 by D31. Similarly, when it is in position to the expression VAB is given by 1 by 2 by epsilon naught QA by QA into log of, okay, it is in second position right now. So that's why log of its distance with respect to B conductor is, okay, 3, right? If you see, so now in second position conductor A is here. That's why for B conductor with B conductor it is at a distance of 2 3, right? So D23 by R small r plus QB is given by log of small r by capital D 2 3, the same term. Next to QC, so with respect to QC, that means third conductor from AB conductors, right? AB conductors are in second and third positions. Okay, C is in first position now. So that's why the term is given by log of D31 by D12. Now, similar manner, when the third position is considered, VAB is given by 1 by 2 pi epsilon, okay, QA log of. So, here now, A is in third position, it completely down. So, B is up, right? It is in first. So, capital D 3 1, right? By small r and QB into log of small r by capital D 3 1, same term. Next, QC is given by, okay, conductor C distance with respect to AB conductors. So it is given like this. Now these are the voltage difference between AB, okay, when they are in position 1, 2, 3. Now to know the overall potential difference, how to calculate? Take the average, right? Take the average value of VAB of these three. So that's why it is shown like that. VAB1 plus VAB2, VAB for first position, second position, third position by 3. So we will get finally, okay, similar terms, okay, are shown here log, right? So with respect to log, they become like this, okay. uh, so 1 by 2 pi epsilon naught QA into log of, okay, D1231 whole power 1 by 3 by R plus QB into log of smaller by, okay, whole power 1 by 3. Now, so 1 by 2 pi epsilon naught, 1 by 2 pi epsilon naught QA into log of, okay, D12, D23, D31 whole power 1 by 3 is taken as D equivalent. D equivalent. So that is written as D equivalent by R plus QB into same term here also. So D equivalent. Now QA plus QB plus QC is equal to 0. So uh, okay. After this, what they have done, this is expression for AB. Similar manner, they have written expression for AC. Okay, expression for AC also. Okay, so it comes QA and QC. Okay, so now add this two. Okay, add these two. VAB plus VAC. Finally, we will get the expression as 3 QA by 2 pi epsilon log of D equivalent by R. Okay, that is our final expression. Now, for a balanced three-phase system, we know that VAB plus VAC is given by, like previous symmetrical case, the same thing we have considered. 3 VAM, right? 3 VAM. Okay, that is what here a system, three-phase system, balanced system is shown. Okay, now, so from the two equations, from these two equations, okay, what we will write it as, okay, on the right side terms, we equate to both 3 VAN is equal to 3 QA by 2 pi epsilon log of D equivalent by R. Okay, 3 gets cancelled. Finally, VAN is given by, okay, QA by 2 pi epsilon log of capital D equivalent by R smaller. So now, this is a potential voltage expression. Now, finally, we calculate the capacitance, right? So, based on the per phase capacitance, we are calculating, let us say for phase A, so QA by VAN, QA by VAN, so 2 pi epsilon, if we substitute that expression VAN, uh, so we will get it as 2 pi epsilon by log of capital D equivalent by R. So if you remember the same expression, okay, for the single phase line also, and for the three phase line with symmetrical spacing also. This is per phase capacitance, okay, 2 pi epsilon 2 pi epsilon naught by log of capital D by R. Here capital D is here D equivalent, which is given by cube root of D1 to D2 D3. Okay, if it is equilateral spacing, all are equal, so it becomes simply D capital D here. So this is how the expression is given. This is given with log base 10. Okay, finally charge current. Okay, is expression is given. So this is for a three-phase line capacitance expression. So these are my references. So from the textbooks, I have taken this. I have prepared this PPTs. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.